can't see from where you are. Did you get it? Okay, cool. Let us begin. Heavenly Father, we thank you for this day. I thank you for these students. I just pray that you just help us to learn what we can today in this room. And I thank you, Lord, for your many blessings. Amen. All right, so I wanted to show you an example of projectile motion. That's a little bit different. So here we go. Let's suppose that this height is h, and you're, I don't know, you got some cannon. And, I don't know. You shoot the cannon at some fixed velocity v naught. All right. So this is an example, of course. And I don't know, whatever you're shooting. What do you guys want to shoot from the cannon? A cat. All right, I'll take it. So the cat. Lands over here and explodes. I mean, it's an explosive cat. So the question then is, if we're launching this cat with initial velocity v naught and angle theta above the horizon off a building of height h, then what theta maximizes the range? Now, in order to actually solve the problem, to find a specific angle, I'll have to put a specific numerical value in for h. But I don't want to do that at the start. I just want to work it symbolically for a while. Then, once we get so far, we'll choose a value for h and a value for v naught and see what happens. Okay? So what are the equations of motion in this case? Projectile motion. So we have constant acceleration of minus g in the y direction. And our equations are what? We've got x is equal to, I'll put the cannon where it fires from, right at, let's say x equals to 0 is here. So that way I don't have to do anything with x naught. So I got x is equal to v naught cosine theta times t, right? Give you a constant velocity motion in the x direction. There's no acceleration in the x direction. So whatever speed it has to start with in the x direction, it just keeps going with that particular x velocity. On the other hand, y is equal to, what do we got here? H, the initial height, right? Plus v naught sine theta times t minus 1/2 gt squared. All right. Of course, that's the y at time t. So how do I figure out the range? So the range is going to be this distance, r, which is a function of theta, by the way. Right, so what's the range as a function of theta? What equation do I need to solve?
You need to solve y for
Yeah, right. I need to solve for y equals to 0. Well, last time I did this, I did some sneaky stuff based on the symmetry of beginning and ending at the same height, and based on the maximum time being, the time to the top being twice the total time. I mean, twice the top time being the total time. None of that stuff is valid here. That symmetry is broken because we're starting with a building. So I have to do the math. I got no choice. So right, straight up I got to solve this quadratic equation.
Professor,
Yep.
couldn't you make it easy on yourself and just raise your reference axes up to the height and then just subtract their half height afterwards?
Well, that's a different problem.
But like theoretically couldn't you do that?
But it's still complicated what happens after we get to that height.
It would be.
Yeah, I mean, all of the complications shifted into how far it would go once it gets to here. You still got this piece to analyze, which is complicated, even though, yeah. And if we think about the problem of maximization, then we'd have to simultaneously think about maximizing the first and the second leg of the journey. Then I'd need two variables. I'm not saying you couldn't do that. Well, I'm going to do it this way. Now, which is often what I was told in college algebra. I would often ask the question to the teacher, could we do such and such? And I usually was given the response, yes, James, you can do that, but we're going to do this. So, so t squared minus 2g v naught sine theta over, oh, sorry. What I'm trying to do is solve, I want to take this whole thing, right, and just basically divide by minus 1/2 g, right? So if I divide both sides by minus 1/2 g, of course I get t squared. For this term, I get what? I get 2 v naught sine theta. Oh, the g is downstairs, isn't it? And then times time. And then what? Minus 2h over g equals to 0. Am I right? You guys agree? Disagree? What do you think? What's that?
You just manipulated it just to make it look different.
Yeah, because I have an easier time completing the square once I've solved for t. So to complete the square then, I've got t minus v naught sine theta over g, quantity squared. Then what? Minus v naught squared sine squared theta over g squared minus 2h over g, excuse me, equals to 0. So cleaning that up a little bit, I've got t minus v naught sine theta over g, quantity squared, is equal to, let's see here, I apparently have got a v naught squared sine squared theta plus 2hg, all divided by g squared. Bring it to the other side. Okay, so then I can solve for t. T is going to equal to v naught sine theta over g plus or minus 1 over g times the square root of v naught squared sine squared theta plus 2hg. Yes, sir. Algebra? I mean, completing the square. So this is a 2, right? So I take this, I divide by 2, which gives me that, right? And so the thing is, if I square this out, I get back t squared, right? And then minus 2, this term, right? But to be fair, what did I do? I added a v naught squared sine squared theta over g squared. So if I added it and it wasn't there to start with, I must subtract it. This is called completing the square. And then this minus 2h over g rides along. These are the algebraic steps which are required to solve the quadratic equation. It's useful to us here because now we have this nice formula for t. Of course, the plus and the minus we can understand, right? This is the t plus, right? And t minus is what would happen if we followed this back hypothetically over here, as if it were launched from the ground. Now, so now that I have this, which one am I? I'm interested in the plus solution, right? So I just got to go and plug that in to the x formula, and bam, I'll have the range. So the range is apparently v naught cosine theta times big parentheses v naught sine theta over g plus 1 over g square root of v naught squared sine squared theta plus 2hg. Let me clean that up just a little bit for our future purposes. So what we really have is that r as a function of theta is, what we got? We got v naught squared sine theta cosine theta plus the square root of v naught squared sine squared theta plus 2hg divided by what? G. So what did we have before? How did this work out when we did it before? When h is equal to 0, what do we get? I'm slightly concerned because I know in h equals 0 case, the formula is what? We derived that last time, right? Right. Yeah, this is wrong. Why? Something I haven't talked about in here too much yet is the idea of dimensional analysis. It can be useful to you when you're analyzing a physical problem and something goes wrong. Now, how do I know there's something wrong with this formula? One of the advantages of not putting in numbers and working with symbols is you could compare things. On the one hand here, I've got meters squared per second squared, right? A velocity squared, divided by g, divided by meters per second squared. The second squareds cancel, and I'm left with meters squared over meters, meters. This term is good. This term, on the other hand, is dimensionally inconsistent with this, you see, because here I have meters squared per second squared. Here I've got a square root of meters squared per second squared, which would be like meters per second. Also here, this is dimensionally consistent, again, with this. I mean, these added together make sense. These are both meters squared per second squared when you look at the dimensions or the units. Yes, sir?
You went from that step to that step.
All right. Which one? There's so many steps.
Did you just, the last one out. Did you just distribute the v naught cosine theta?
Ah, thank you. There it is, right there. So I neglected to multiply this by that. So it's easy to fix. Thank you, thank you. So if you've been otherwise careful, there's no need to throw the baby out with the bathwater, as the saying goes. You just gotta take a step back and find out what you did. In this case, I forgot to multiply by v naught cosine theta. Now, once I do that, we're good to go. See, because with that correction, now I've got the right units. And you see what happens when h equals to 0, this term drops out. And what do I pick up? I pick up twice v naught squared sine theta cosine theta in concert with what we did last time. So that makes sense. All right. Es bueno. All right. Now, past this point, I don't like to do analysis on this problem in general because it's kind of a drag. But let's look at a specific. Let's put in some numbers here and do some analysis. We'll let Wolfram Alpha help us out a little bit here once we get a bit more into it. So let's choose some values. So for V naught, let's let V naught equal to what? Would you say 1 meter per second? Thank you. Much obliged. But let's make h interesting. Let's make h equal to 3 meters. With those, with that, what do we have? We have r of theta is what? 1 squared is easy to calculate. We got sine theta, cosine theta, right? Plus cosine theta times what? Square root of, yeah, sine squared theta plus what? Oh, did I say that h was 3 meters? What I meant to say was that how did I say this? H was actually equal to 30 divided by 9.8 meters. There we go. Well, isn't that convenient? So that g cancels the other g. What do we get? What's that? 60. That seems a little big. Let's make that a 3. No. A 6? Make this a 6? I'll take a 6. I wanted to make it interesting, but not too interesting. 6. So that makes this plus 12. All right. And then, of course, all of this is divided by what? 9.8. So if you don't mind, well, fine. There. Happy. All of this is in meters. Maximize the range. I didn't actually have to give us V naught. You know, guys, I could have just left. I could have left V naught as a constant. We could still do it with V naught floating around as a constant, but it's a little bit easier to see our way through this way, so I did it. So what's dr d theta? I am serious. Let's see here. So that would be cosine squared theta minus sine squared theta, right? And then minus sine theta square root of sine squared theta plus 12, right? Minus sine theta cosine theta, rather plus sine theta cosine theta, I should say, plus sine theta cosine theta divided by 2 times the square root of sine squared theta plus 12. That is the derivative. Chain rule, product rule, it's glorious. And then, to find the critical angle, you have to solve that equal to 0. There's no reason that should be 45 degrees. None at all. But that critical angle gives you the maximum range. And the only way you can really figure that out is to do dirty numerical method stuff. Because this is a real world problem. Right? And that's the nature of the beast. We are not alone. Wolfram Alpha will help us. Wolfram Alpha was born for this. I have made this homework in previous semesters. They don't have this in WebAssign though. Oh well. Some reason. Oh, yeah. I must adapt. Silence, computer. Now, the reason I did that derivative was to convince you that you didn't want to do it. Let us now look at sine x times cosine x plus the cosine of x times the square root of sine squared x plus 12 and let's see what Wolfram Alpha interprets this as. Whatever. That's just a rescaling of the graph. We don't want to confuse Wolfram Alpha, you know? Now, of course, what matters here Mr. Smarty Pants here has given us a graph for lots of different angles. The only ones we really care about are what? Yeah, between what? Between 0 and maybe 180. Probably 0 and 90 are most interesting to us. So if you look at this, here's pi, so 90 degrees is in here somewhere. So it looks like it's up in here somewhere, right? Now that won't, I mean, that gives you a sense of where the answer is. To actually find it, you gotta be a little bit more creative. How about maximum of no global maximum, fine, whatever. I don't care. Just give me the first one. So, about here. So let's see here. That's radians, right? So how many degrees is that? 0.27 radians. How many degrees? Oops, other way around. I forgot my calculator. 15.47 degrees would maximize the range given that initial velocity and that height. So it's considerably more shallow than 45 degrees. Maximizes the range in this case. What's that? I don't know. We'd have to go back and try a different one. You get a different function, you get a different maximum. It's complicated. Right? So, yeah. It's not so easy to be an artillery person, is it? It's actually a little bit harder than it looks, right? There's some thinking required. I wonder how they solve these things real time on the battlefield. They don't? Yeah, probably not. Yeah, fine, they've got computers. Why do we even come to school? Why don't we just use computers? Forget understanding anything. Why are we here? I don't know. Let's just go home. Sorry. I know what you're saying, though. You're of course right, but...
Back in the day.
Yes, back in the day. Imagine that the robots have gained consciousness, and it's after synchronicity. You find yourself in the position of needing to combat the robots without being able to use computers. Then you'll die. Then you won't have a sequel. No, but okay, I digress. All right, so Anyway, there's a more complicated example of projectile motion I thought we should spend some time on. So now we have, and we'll move on. All right, so what's left for today is I want to talk to you guys about relative motion and then a little bit about force. So let's talk about relative motion. Is it okay if I erase all this stuff? Well, anyway, I'm going to. Yeah, my luck is when I make up specific numerical examples for people doing homework, I will inadvertently choose V0 and H such that the maximizing angle is like 44.4 degrees or something stupid. So that's why I wanted to be careful in my selection here as to actually illustrate the phenomena significantly. I'm happy with our choices. All right. So this is relative motion. So here, basically our goal, it's pretty simple, although it's not, is to compare velocity, position, even acceleration for different observers. So observers, what in the world is an observer?
You're talking about like related rates?
Yes, but not that kind. I mean, we will be relating rates, so I can't. Not really.
People looking at it from different places.
Right. I mean, the point, yes, the reference frame we talk about. Everything we've done up to this point is implicitly been with respect to what?
X and Y.
X and Y, right? Some system of coordinates. So what's the built-in assumption there is that you can pick an origin, right? And you can lay down some system of measurement where you can measure distance in terms of 3 rectilinear Cartesian coordinate system, right? From that point. And also, somehow magically, you can keep track of, I mean, not really magic, it's just complicated. You can keep track of where things are at specific times, right? And also that, there's this sort of universal concept of time which is everywhere. We kind of just even take that for granted. But an observer is basically a system of coordinates, right? That can observe events that happen at given times. Now, so behind this, we can think about 2 different observers. So like here's, say, Z bar, Y bar, X bar. And then there's another system, the first one really, Z, X, and Y. And so I have 2 different observers, S and over here S bar. And you can ask, if we think about 2 different frames of reference and we compare them, how do the positions compare? How do the velocities compare, and so forth? And given that we've got this universal background time, which is shared by everybody, it's not that hard to understand. First of all, we have to come up with a notation. So like basically I'm going to say that this vector here, this red vector, is, we'll call R0. R0 vector. So R0 is the position of the S bar origin in the S frame of reference. So far, so good? Are we agreed? Does this make sense? You could think about it? Gentleman in the back in the green shirt. What was your name again? Matthew. So like Matthew could have another coordinate system. And I could have my own coordinate. We call Matthew the bar coordinate system. I'd be the regular coordinate system. And then Gentleman over there in the front, what's your name? Will. We could compare Will's position in my frame of reference versus your frame of reference, right? You would say he's at a different position vector than I would because we've got different origins, right? Now, and in general, maybe your z-axis could be tilted or something. That would be even more complicated to try to compare them. We'd have to think about rotations and such. So in order to compare things, we need something to compare to. So what we then, a third thing in this story, we've got the position of some object. Some object, okay? And we can compare the position vector for that. On the one hand, we can look at it from the unbarred coordinate system. We can call it R. And I'm sorry for what's about to happen. It's a necessary evil. And then, on the other hand, we could look at it from Matthew's coordinate system, like so. And this would be, yeah, I know, it's awful, R bar vector. My point is that's the position vector with respect to the bar system. That's the position vector with respect to the other coordinate system. How are these related? R bar vector is equal to what? I mean, what equation can I write that? Let me write an equation which is clearly true from vector algebra, and then how about this? R naught plus what? R bar vector is equal to what? R, right. So there's our first relation. That's the relation between the position in the S frame and the position in the S bar frame. To get the position in the the S frame, and for the sake of discussion, let's think of the S frame as the rest frame. Let's think of this as being at rest, and let's think of this one as being moving. That will help the language here a little bit. Right. So if I want to know, what's the position in the moving frame? Excuse me. If I want to know what the position is in the rest frame, I take the position of the origin of the moving frame, and then I add the position of the object with respect to the moving frame. There it is. So far, so good? Okay. Almost no one asks you a question about this. What they invariably ask you a question about is velocity. So how do you get How do you get the relation between the velocities? You integrate. Shut up. Very funny. Okay, so dr naught dt plus dr bar dt is equal to dr dt. Because there's this one universal time that both frames of reference use. So we can measure the instantaneous rate of change of all these with respect to, and so what we have then is we've got the velocity in the S frame, right, is equal to the velocity of the origin in the moving frame plus the velocity as measured by the bar frame. For example, if I've got a train, I don't know, it's a weird train. There you go, whatever. And it's going this way at 50 miles per hour, right? And I think about, okay, I ordered a coordinate system from the store and I stuck it on the train right here. All right. So here's my moving coordinate system. I just based it on the train right here. And then if I, well, for lack of imagination, I stick my cannon here, all right, and I shoot a cat, since that seems to be our, well, it hasn't exploded yet, it's still alive. Let's see here. And I shoot this cat from the cannon at, say, 40 miles per hour at an angle of, what do you want? 30 degrees? Then I can ask the question, what's the velocity? Now the velocity, when I say 40 miles per hour at 30 degrees, I'm talking about with respect to the train frame. That's with respect to the bar frame. According to the specs of the cannon, it will shoot a cat that fast if you put it at that angle. We looked at the instruction manual, that's what it said. All right. Then the question then, of course, is what's the velocity of the cat with respect to the rest frame, with respect to the ground frame? So as we're just watching, if we're observing the velocity of the cat, you know, from the sidelines, what is it?
Wouldn't the x component be whatever it is in the moving frame plus 50, and then the y would be just whatever the sine 30 is times 40?
Right. So, but here's how we do that. I mean, let me relate it to this. So V naught, right, is 50 miles per hour, 0, right? Because it's just moving in the x coordinate direction that way, right? The velocity of the cat with respect to the bar frame is 40 miles per hour times the unit vector, what, cosine 30 degrees, sine 30 degrees, remember that? There's a vector in that direction, whatever that is. I need to calculate. Can somebody calculate that for me? The other one is 20, but the y component is 20 miles per hour. The other one I need help with. What's 0.866 times 40?
34.64.
34.64. So there's the velocity of the cat relative to the train. Then to find the velocity of the cat right as it leaves the barrel, right before it explodes or whatever. Sorry, cat lover. You should have taken Mr. Omby's section. It's too late now, I guess. Let's see here. V naught. So we add these. And what do we get? Just what the gentleman said at the start, we just add the x velocities, 84.64 miles per hour, and the other one we get 20 miles per hour. And so there you go. Notice that the angle's not preserved. I mean, the angle is 30 degrees with respect to the train, but if you calculate the angle, the standard angle with respect to the ground here, you don't get 30 degrees, you'll get something else.
Because it factors in the height of the train?
Because the x component of the velocity is longer, because it gets the 50 miles per hour as well. Yeah. Right. So I'm using this, I'm just adding like that. Now, typical problems you have in your homework are stuff like some guy's swimming across a river, the river is going one way, so what you got to do is you add the velocity of the river to the velocity of the swimmer relative to the river, and that will give you the velocity of the swimmer relative to the shore. That's how the problems are done. Or there's another problem, I think, where you have a moving walkway, right? If you walk with the walkway, you add the velocities. If you walk against the walkway, you subtract them. I mean, we've all gone the wrong way up or down elevators, right? I mean, escalators, you know what I'm talking about. Your mother told you not to. You didn't listen to her, you did it anyway, right? I can tell you're the type. Can see it. I know it. I did it too. Let's see here. I was a bad son. Oh. So what else do we care about? One more derivative, ddt. What do we get? Yeah, so I'm going to be lazy and just put squares on this. So that gives us that the acceleration, as measured in the rest frame, is equal to the acceleration of the origin of the moving frame plus the acceleration as measured with respect to the moving frame. This is A naught. This is A S bar. And this is just A with respect to the rest frame. So the accelerations add in the same way. So if you could sprint, right? If you could sprint with an acceleration of like, say, half g, I don't know, that's probably ridiculous, all right? And if you were on a train that was also accelerating at a half g, right? And the train accelerating at half g didn't affect your ability to sprint at a half of the, half g, then your acceleration with respect to the ground frame would in fact be g. The accelerations add in the same way. On the flip side, something more interesting, what happens if the origin of the moving frame is not accelerating? Yeah, okay, for my example, I'm sorry. Thinking more abstractly, forget my example. This formula in general, if A naught is 0, the acceleration of the moving frame matches the acceleration of the rest frame. Now, why is this interesting? That brings us to our next topic, which is forces, right? So, what is the concept of, so up till now, all I've really done with you is I've discussed given an acceleration, or given a position as a function of time, or given a velocity as a function of time, or given some vectors, how do you add them, subtract them, do math to them, basically, right? We have not really answered the question, why is the acceleration what it is, right? I just told you the acceleration is minus g, right? So now we come to what's called the study of dynamics. Dynamics is not just the study of, how the equations of motion are solved. Dynamics is the study of why there's motion. And the why comes from something called a force. So the idea is that there are these things called forces, and the forces cause the motion, all right? So like, for example, the force of gravity. Causes gravitational motion, acceleration. Or another example, the spring force causes spring motion. Let's see here, are there other examples? Yeah. Oh, rockets. You could have a rocket. Rockets thrust, right? Makes rocket accelerate, right? This is just a couple of examples. There are more. Now, how's that work? I mean, basically this is the definition of force, all right? And so the idea is simply this, is that in all of these cases, the force is equal to the mass times the acceleration. So there's these things called forces, right? And for a given force, it will cause an acceleration on an object, but it's not the same for different objects have different masses. So for a given force, the more mass that object has, the less acceleration will actually get produced by a given force. So there's this, or you could rewrite this perhaps more descriptively like this. The acceleration is the force divided by the mass. So like for a given force, the acceleration which is produced will be larger or smaller depending on whether your mass is larger or smaller, right? You've experienced this, right? If you happen to run into a football player in the hallway, you don't move much. If you happen to run into someone who's like 5'1" and weighs like 90 pounds, it might be bad, right? I mean, I think that's a relevant comment to all of you. I don't know, what's that?
So a cheerleader?
Yeah, sure, a cheerleader. Is that the specs on the cheerleaders now? I don't know. What's that? On the flyers. Okay. Now each one of these comes with a specific, these are like people. They're different. And they kind of each have their own identity. Gravity, close to the surface of the Earth, the force of gravity is equal to the mass times this constant g. A little bit later, we'll learn that the real formula is gm, big M, divided by r squared. But, later. Still just the, that's just the magnitude of it. Let's just talk about magnitude here for a second. Spring motion, the force for a spring is equal to minus kx. So here, the way that works is you got a spring, it's got some equilibrium position, say x equals to 0. And what happens? If you stretch out the spring, like that, suppose it's tugging on some mass m, then you'd have x greater than 0, right? So the spring force wants to do what? Wants to pull it back to equilibrium, right? So that's why there's a minus here, because if x is positive, the force should point to the left. Likewise, if the spring gets compressed, x is negative, and the force points to the right. Minus minus is plus. That's a spring force. This is a pretty good approximation for some materials. There are some materials which basically behave this way. If you put them in a coil, to a good approximation, they actually do satisfy this for some particular constant k, which is a characteristic of the material. Not quite true for like a rubber band. A rubber band has a different force displacement characteristic. We have a lab where we look at that. A rocket's thrust, well, that's kind of that I don't have a formula for that. That would be, sometimes I might give you some kind of problem. Like, here's an example. You got some dude. So we get a cat. And it seems like he's more of a rat this time, sorry. And I don't know, you put him on a couch. Right? But then, affixed to that couch are rockets. And you could say, suppose the couch has a mass of 50 kilograms and the cat has a mass of 10 kilograms. And then you can ask fun questions like, if this provides a constant thrust of, say, 10,000 newtons for, say, 1 minute, then how high does cat go? Now here I'm assuming something very convenient, which is that we can neglect the mass lost as the rocket's thrust. If we think about variable mass problems, that's harder, all right? How would you solve a problem like that? Differential equations, no. No. Oh, I'm sorry. For the mass loss problem, you're absolutely right. Differential equations is the right answer to that. So for something like that, what I need to do is figure out so here's the deal. Newton's second law says what? So I told you guys about some particular let's say, people that can join the party. But the party is not complete until you know everybody at the party. And so that's where Newton's second law is about. Newton's second law, it's party, force party. And we got the net force is equal to the mass times acceleration. It's important that it's the net force. Only the net force, the total force, is equal to the mass times the acceleration. So these comments I was making before are really, I'm assuming that like the only force at play was the spring force or the other one. It's also important that this is a vector equation, more generally speaking. Now, I'm going to talk about this example just for a few more minutes, if I'm not out of time. Time flies when you're having fun. Oh, we have time. So let's just, we'll have to get back to the vector. The fact that this is a vector equation cannot be neglected, generally speaking. But for this example, we can just think of this as a vertical example, right? So that vector equation just is in the vertical direction. So we can kind of neglect the vector aspect here for a second. All right, so continuing this example. So let's say that A is equal to, we're looking at a one-dimensional problem, is my point. In the y-coordinate, all right? And I'll let y be up, the usual thing. So the acceleration is equal to what? Mass times acceleration is equal to what? It's equal to the net force. What's the net force in this case? So sometimes we can visualize the whole thing as a point particle. So this whole system I just think of as one point mass. What's the mass of the system? Yeah, m is equal to m1 plus m2. So that's a really nice thing about physics, is it allows us to not think about the cat and the couch separately. We can think about them collectively as a single thing. It's very fortunate that physics works this way for us. You could imagine God created a universe where that wasn't the case. It would be more complicated, the laws of physics. Now, so the thrust force is like this, right? I'll call it Ft, thrust force. Force of gravity, which direction does that go? Down, right? So this is minus mg. Sometimes I write the minus, sometimes I don't. You should understand it goes in that direction with magnitude mg. Now, ambiguities about signs have to be gone by the time we get over here. So what we've got the thrust force minus mg. This is called a free body diagram. So it's our first free body diagram. A free body diagram, all that means is you draw a point, or you could also affix the vectors to a picture of the thing you're looking at, and you put in all the forces that are at play. So it's a way to collect our thoughts about who's at the party, let's say. In this case, it's just gravity and the rocket. We're neglecting other things like friction. All right, so then what? Put in the numbers. We got what? We got 60. A is equal to 10,000 minus, what is it? Mg was 60 times 9.8. All right. Now I threw out the word Newton. All right. So what is a Newton anyway? I mean, I should tell you that, I suppose. Unit of force is N for Newton, and that's a kilogram meter per second squared. for Newton. That's what it has to be, right? Because if F equals ma, we've got mass, which is kilograms, times a, which is meters per second squared. So the units for force have to be kilogram meters per second squared. If you don't mind, I'm going to omit the units until we get to a good place to put them in. So A is what? A is equal to, goodness gracious, 10,000 minus what? Minus 60 times 9.8 divided by 60, which is what? Man, I thought I had my calculator on me today. I'm annoyed. I guess there's probably, yeah? 156.9 meters per second squared, right? Because I did everything in kilograms, meters, and seconds, and so forth. Yeah. Oh, it's okay. Thank you, though. I may take you up on it. Oh, you just, yeah. Well, you better hold. I'll lose it for you. I don't want to. All of a sudden, I'll lose it. How high does it go then? Well, see, now we're back to the stuff we've been talking about already. Kinematics. Kinematics is just the study of motion without regard to why. The answer to the why, of course, is, well, there's these things called forces. Now, I mean, we've really just traded one mystery for another, right? Where do forces come from? Why are there forces, you know? You know, one deep mystery is, why is it that certain forces seem to have a dependence on mass, like gravity? The force of gravity depends on mass, right? Spring force doesn't. Lots of other forces don't, but the gravity force.
Like, why do some have force carriers?
I don't know the force carriers, but
A lepton?
lepton. No, it's something more. I mean, this is, why is there a mass depend? Why does it depend on mass? This force of gravity. See, mass over here is something inertial. It describes how much of force actually produces motion. Some kind of proportionality constant, which says you get smaller acceleration for a given force. Why should that have? Why should?
Byproduct of that, because of all the major forces, we haven't discovered a lepton for gravity. So hypothetically, if there was one, that could be the explanation, but we haven't found one. So.
Oh yeah, but I'm talking about something less out there at the moment, which is just, I mean, it's just an observation you can make. This has to do with inertia, the object, you know, the tendency of an object to resist a change in motion. This is, why should this have any? Why should that proportionality constant, the same m, be here and here? That's a mystery. It's a mystery that's kind of been answered by general relativity, but it's a mystery at this point. Now, how high does it go? I'm assuming it starts from rest, right? So we know the acceleration, right? We know the acceleration is 156.9 meters per second squared, right? We know that V naught is equal to 0 meters per second. We don't know VF, you know? But I guess we could figure out VF pretty quick, couldn't we? Let's do that. What is VF? V naught plus the acceleration times the change in time, right? We know the time we're interested in, right? Oh, I'm sorry. There's really two steps to this problem. I guess let me ask a slightly simpler question. How high does the cat go at t equals to 1 minute, all right? What would we have to do? If you think about it, what I'm about to find is just how high he gets to when the rocket turns off.